Hello and welcome to Logical Verification 2020-2021. This video is about Chapter 11, Section 5.1, the construction of the integers. The integers are an important data type, they are an important structure in mathematics. You all know them, they are the numbers, the infinite set of numbers, minus 3, minus 2, minus 1, 0, 1, 2, 3, and so forth. And the question is, how do we construct these numbers in Lean? In the previous two videos, we've looked at how quotients and subtypes work like in general, and now we are going to look at how to use them to define something interesting, like the integers. Okay, so this is an important construction. We will see it again in chapter 13 for more complicated objects. So I think it's a good idea to do this carefully now. Okay, so one way to think about the integers, a very important way to think about the integers, is to think of it as the integers as the natural numbers plus the operation minus. Essentially, the integers are what we get when we take the natural numbers and add all the elements that are necessary to make subtraction work. Okay, so in a certain sense, every element in the integers is a subtraction of natural numbers. It can be represented as a subtraction of natural numbers. So every element in the integers is a subtraction of natural numbers. So quite literally, the integers are really just the elements that we obtain via subtraction of natural numbers. I mean, you can verify this yourself. I mean, any negative integer is 0 minus some natural number. Any positive integer is a natural number minus 0. And so obviously we can obtain every integer using this representation. And adding operations to a structure is something very common. And this is really like the go-to pattern to extend structures by the operations, is to consider applications of the new operations to old elements and then define the type in terms of that. So what we're going to do is we're not going to take this minus because we don't have a minus yet. Instead, we're going to look at pairs AB that stand in for this minus, and then we can define the integers as either a quotient of those pairs by appropriately defining what it means for those formal subtractions of pairs to be equivalent, while keeping, of course, in mind that the pairs just stand in for the subtraction, or by taking a subtype of some canonical representative of the equivalence classes. Okay, so we're going to define the integers as first as a quotient of pairs. Okay, and the pairs, so the pair AB should represent the integer A minus B. So now we need to figure out how should we define the equivalence relation of pairs. Okay, and so what you should keep in mind is that the pairs, they should represent the subtraction. So like this should be A minus B equals C minus D. However, we do not have minus yet, so we need to explain this equivalence in terms of operations that we already have. And if we just add b and d, so b plus d to both sides, then we can transform this into something using just addition. So then we get a plus d is c plus b. Okay, so this is what we would, so this is kind of the idea that we have here. So we in the end, we want the pairs to represent subtractions. And if they represent subtractions, then they also need to satisfy this property that if those two subtractions are equal, then a plus d is equal to c plus b. And so we will use this equation here as the definition of the equivalence relation on the pairs. So we are going to define this here as a plus d equals c plus b. Right? Because it makes sense when we interpret the pairs as subtractions. And this is something that we can really define in terms of natural numbers. This is just a good old natural number. Okay, so this is the equivalence relation that we will use for the integers. And maybe it makes sense to draw this a bit visually. So we have here a, so here a, and we have here b. And the equivalence classes that we get here are approximately these ones here. So we got one here, here. This is 0, this is -1, this is 1, this is 2, this is 3. Okay. So let's look at how this is done in Lean. So first we define a setoid containing this equivalence relation. Okay, so the setoid contains the relation. As promised, this is hard to read, but if you remember what I've drawn, it's exactly the same thing. If it takes the first component of Pn of the first pair and the second component of the second pair, and if we add them together, it should be the same as if we add the first component of the second pair and the second component of the first pair. It's exactly what I've written on the drawing. And now we need to prove that this is an equivalence relation. So we need to prove three things. We need to prove that it is reflexive, that it is symmetric, and that it is transitive. Okay, so this is more or less just routine work. Okay, so now we've defined a setoid on the pairs of natural numbers. And in Lean, it's always a good idea to state such definitions explicitly using calculammers, so that if you define a setoid, you typically write a lemma that says that the setoid relation holds if and only if the definition. This is very helpful because then you have some control over how to rewrite using a definition here. Okay, so just to reiterate, these two pairs are equivalent if we have this equality of sums that I've drawn. And now we can define the quotient using the setoid. It's just the quotient of the setoid, and this is now the integers. Okay, now let's define a few operations on this. First, let's start with the integer 0. So 0 is 0 minus 0. So we write that the integer 0 should be the equivalence class of the pair 0, 0. Okay, so far it's just a definition. Right. So in fact, it does not matter. We could also say that 0 is m minus m. Well, it's the equivalence class of the pair m, m. So let's prove this. So we unfold the definition of 0. We then get that we need to prove the equivalence between two equivalence classes between two quotient make applications. We do this by applying the quotient.sound lemma. Okay, now we need to prove that they're equivalent, and by definition, this just reduces to some equality of addition, which we can easily finish with a simplifier, and then we're done. Okay, so the next thing we're going to do is we're going to lift the operations on the natural numbers to the integers. So we have addition on the natural numbers, which we're now going to lift to the integers. And this works using the quotient.lift2 operation. Addition is a binary operation, hence we use the lift2 function. And okay, so now we need to figure out how to define addition on our new integers, which are represented as pairs. So let us quickly work this out by hand. So what do we have? We want to add, that's the wrong color. So we want to add a minus b and c minus d. So, and this should be a plus c minus b plus d. Right, and so it should also be the same on the level of pairs. So what we actually mean here is that if we add these two pairs together, we want to get this pair here. Okay, so that's how we derive our, well, the definition that we think is the correct one for addition. Okay, so let's write this down. Yes, so this is probably the one that I've written on the previous slide. So okay, so we want to lift this definition on pairs to the quotient. So for this, we need to show that equivalent pairs give equal results. Yeah, so right, if the pairs are equivalent, then the result should be equal. And right, in order to prove that two equivalence classes are equal, we again apply the quotient.sound lemma. And now we need to show that the resulting pair is equivalent. We unfold the definition for the relation on the integers, for the equivalence relation on the integers, and then we just call linear if, because this should be true, and it is also true. Okay, so good. So now again, it's always a good idea to restate your definitions as lemmas. So, okay, cool. So we write a lemma that says what happens when you call int.add on the equivalence class for pair, and then you get the corresponding pair out of it. So you don't need any extra lemma for this. This is always works using graph. Quotient.lift2 applied to equivalence classes always reduces by raffle. And indeed, this is the definition I gave, I drew on the picture. So, of course, there are a lot of properties that we want to have of addition. We want it to be symmetric. We want it to be commutative. We want 0 to be a neutral element, so that n plus 0 is n, and 0 plus n is n. And all of those properties live from the natural numbers. So let us take one of those properties, that 0 plus I is I for all integers. And this is a property that should hold true for all elements of a quotient, so for all integers, and we prove such properties via induction on the quotient. So we do induction, so in induction on I, we apply the quotient of induction on lemma I, and now we've transformed the goal. So right, we started with the goal that says for all integers, and now we transform the goal using the quotient induction to for all pairs. So for all equivalent, for all pairs AB, adding 0 to the equivalence class of the pair is the equivalence class of the pair. Okay, this is much more tractable because now it's no longer a statement about quotients. So we can just simplify this a bit. We can introduce the quantifier. We can rewrite using the definition of 0, and then let's take the pair apart using cases. Again, unfold the definition of equality. And, well, we don't even need quotient.sound here. We could just call simp now. Because, right, we can simplify the left part to p, the right part to m, and then they're equal. Okay, so in this way you can also lift the other operations. So that then you can, the other operations like multiplication, you can define a multiplication of integers. You do this using a very similar recipe as here. You try to figure out what is a minus b times c minus d, and then you just write this down as your new definition of multiplication on the integers. And then you can also lift all the other properties that you want. So multiplication is commutative, that multiplying something by 1 returns the integer itself, and so forth. Okay, so this is one way to define the integers. Another way is to define the integers using subtypes. So what I've shown you here is the way to construct the integers using quotients. So by identifying pairs of natural numbers that have the same difference. So that should correspond to the same integer if you interpret a pair as a subtraction. And another way to construct integers is as a subtype by picking a canonical representative out of each of those equivalence classes. For example, by so which one do we take? So I think it's always a positive 1 and 0 or something. So I think we take this one here. So as a subtype, where we pick for every one of those blue lines a point here as the canonical representative, and then we look at the subtype of these canonical representatives. And right, so there are two canonical representatives, the two cases. One is that the first component is 0 and the second one is greater or equal 0, or that the first one is greater or equal 0 and the second one is 0. So right, it's one of them must be 0 and the other one must be greater or equal 0. So we take this set of canonical representatives, so like exactly one out of each equivalence class, and then we can define the integers as a subtype instead of a quotient. Okay, so we've picked some canonical representatives, and then we look at the subtype. So for this, we need to do, this is in a sense more technically involved. So if you think back at how we did it with the quotient, this was fairly straightforward. We just define some equivalence relation, and then we lift all the operations in a very straightforward way by just figuring out by just essentially rearranging the minus and the pluses in a natural way. While if we want to compute with canonical representatives, we always need to normalize every operation. So if we want to take the addition of two such canonical representatives, we then need to normalize it to get the canonical representative of the sum. And for this, we write a new function which, given any element, so any pair of natural numbers, returns the canonical representative of its equivalence class. So if you give it some element here, then it will return this one here. Okay, now we can prove that we define this normalization function, and we can prove that the result is canonical. And then you can define all the operations like addition and multiplication in a similar way to the quotient construction, except that here you do not use lift, but instead you normalize the result after every operation. So define addition by taking the value of the element of the subtype, adding them in the same way as we did before in the quotient construction, and then normalizing it after every step. The advantage of the canonical representatives construction is that you can easily access the canonical representative. So with the quotient, it's sometimes hard to retrieve the underlying element from the quotient. Like while we can lift functions, so I have the quotient make function that goes from alpha to quotient s, there is no way back. While with the representative approach, it's very easy. Like you always have the canonical representative at hand.